Finally, we're going to get to the end of this. We've been studying systems of linear first order equations that are homogeneous and have constant coefficients. That is, du dt equals matrix A times u, where u is a vector and A is a square matrix. For our purposes, we'll just do 2 by 2 systems, and this all generalizes very easily to larger systems, actually. We said last time that if we had a first order system where the matrix had distinct real eigenvalues, then the eigenvectors are always independent. Eigenvectors for distinct eigenvalues are always independent, and you can immediately write down the solution as a constant times e to the eigenvalue t, first eigenvector plus constant times e to the eigenvalue t, second eigenvector. Then we could apply the initial condition, and plugging in the initial condition gave us a system of linear equations that turned out to always have a unique solution. And in this case, we got those solutions for the constants, so that the differential equation together with an initial vector at any time whatsoever, the initial conditions just have to be at the same time, determines a unique solution in terms of the eigenvalues and eigenvectors. So it's a real nice, easy thing. Now we want to go to the next step. What happens if the eigenvalues turn out to be complex? Remember, the eigenvalues are the solutions of the characteristic equation, which is a polynomial equation. And in a 2 by 2 case, you get a second degree equation that can have, by the quadratic formula, 2 real solutions that are distinct, 2 real solutions that are equal, or 2 complex conjugate solutions. What if you get 2 complex conjugate solutions to a first order system that's homogeneous and linear with constant coefficients? Here's an example of what happens there. Let's first say what happens. Without going through the extended theory, I'll just say that when you get complex conjugates, the things we proved before still hold. E to the eigenvalue t eigenvector is still a solution, and because the eigenvectors are always distinct for a complex conjugate pair, you get 2 independent solutions always. So what's wrong? It's not wrong if you're solving for complex valued vector solutions, but who wants to say the spaceship went off into imaginary space, right, when we got imaginary solutions? Right, so these will be complex conjugate solutions with, in general, an imaginary part. And the thing is, you can glean real solutions out of these because the real numbers are a subset of the complex numbers, right? They're the subset that has imaginary part at 0. So if we write all linear combinations of solutions of this one, which just like in the previous problem is, right, this was the theory we proved before. If you have, in general, an n by n matrix and a vector of length n, a constant times e to the eigenvalue t eigenvector plus dot 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 constant e to the eigenvalue t eigenvector is the general solution when you have n independent eigenvectors, we said, right? So it works in the complex case. It's just that it gives you all complex value vectors. You want to restrict to the subset of those that are real valued. So how can we do that? Let's go back down. What we can do is this. We remember that theorem that says any linear combination of solutions is again a solution. So in particular, if I take 1/2 times the first solution plus 1/2 times the second solution, that must be a solution. But what's 1/2 times the first solution plus 1/2 times the second solution when these are complex conjugate solutions? Well, it turns out that the imaginary parts cancel when you do that, right? Because they're complex conjugates of each other. This one has real plus I times imaginary part. This one has the same real minus I times the same imaginary part. When you add them, the imaginary parts cancel. You just get 2 times the real part. Times 1/2 gives you the real part of the first solution or of the second. They're the same. And what this shows, since any linear combination of solutions is a solution, is that the real part of the first solution is a solution. Similarly, if you take 1 over 2i times the first one minus the second one, well, this is, now the real parts cancel because you got real part minus real part, the same real part. The imaginary parts are minus each other, right? One of them is a real part plus I imaginary part, the other one is the same real part minus I times the same imaginary part. Just because V1 and V2 are complex conjugates and alpha plus I beta and alpha minus I beta are complex conjugates. These two things are conjugates of each other. So the real parts are equal and their imaginary parts are minus each other. So when you subtract them, the real parts cancel and the imaginary parts combine to give I times, or 2I times the imaginary parts. Well, if you divide by 2I, that leaves you with the imaginary part of either the first or the second one you can use. Imaginary part of the first one is what you get when you divide by 2I, or minus the imaginary part of the second one. And that must be a solution because it's a linear combination of solutions, right? This constant times this one plus the same constant times minus this one. And so we find out that the real part and the imaginary part of either U1 or U2 in the complex case are actually independent solutions. And so you can also write it this way, e to the alpha t cosine beta t, real part of V1 minus sine beta t, imaginary part of V1, and then same thing here with imaginary real and plus. But that's what you can do, is just take the real part and the imaginary part of either vector and get a solution. So let's try that here. Oh, and the point of this is that now look at, these are real valued functions. So we found two functions that are real valued that are also solutions. If we take the arbitrary linear combination of these, we'll also get all solutions. But, let's go back up here. If we use those two solutions, real one and a real one, how can we get all complex solutions? Well, it's because in the general solution of our complex value functions, the constants that multiply can be arbitrary complex conjugates. So just like here, this gave you all complex solutions when you let alpha 1 through alpha n be complex. When you use the real solutions here and let these be complex, you still get all complex valued solutions. But now, the real valued solutions are the subset where you restrict alpha 1 through alpha n to be real numbers. So when you choose, instead of e to the eigenvalue tv1 and e eigenvalue tv2, the real part and the imaginary part of the first solution, those are independent solutions. This still gives you the general solution, and the set of real valued solutions is evident by restricting to constants that are real to multiply them. Alright, so that's it in a long mouthful. Let's go to the example finally. How about this system? ddt of u1, u2 equals 2, 1 minus 4, 2 times u1, u2. Here's a linear homogeneous constant coefficient system of two equations and two unknowns. If you work this out, maybe I should do it here, huh? We haven't done complex eigenvalues and eigenvectors, but here's how it works. Eigenvalues and eigenvectors are complex conjugates. We find them in exactly the same way. We just need complex arithmetic. Here's the matrix we had, 2, 1, minus 4, 2. How can I find its eigenvalues and eigenvectors? I would just write down the same eigenvalue equation. Determinant a minus lambda I equals 0. That means I write the matrix A, but I subtract lambda from each diagonal element, remember, all equals 0. The determinant is this diagonal, 2 minus lambda times 2 minus lambda, minus this diagonal, minus a negative 4 times 1, which comes out, when you multiply it out, to be lambda squared minus 4 lambda plus 8 equals 0. Now we can try and factor that all day by guessing what goes in the blanks, but it's probably going to be difficult for us. When this comes out that you get complex conjugates, you usually go to the quadratic formula. Alright, we'll say lambda out of this equation must be minus b plus or minus square root b squared minus 4ac all over 2a. And when this is the square root of 16 minus 32 square root of minus 16, well, square root of 16 is 4, square root of minus 1 is I, so this is 4i. And here are our complex conjugate eigenvalues, 4 plus or minus 4i all over 2, found by the quadratic formula. is 2 plus or minus 2i. So we can call this lambda 1 and lambda 2 our two eigenvalues. When they're complex conjugates, in some ways finding the eigenvectors is easier, even though you think initially complex arithmetic, right? But we solve the same equation, a minus lambda times the identity u equals 0. Here I'll put lambda 1 here, so I'm finding an eigenvector u1 that goes with it. Well, what's a minus this times I? You subtract this from each diagonal element, and you get this matrix times u equals 0. This matrix, 2 minus 2, is nothing. Minus 2i leaves us minus 2i. And the same thing here, minus 2i. So I get this matrix times u equals 0, which I've written in the augmented form, right? So here's the matrix I get by doing my subtractions in here, times u equals 0. Now you remember, if you don't make any mistakes above, that the second row will always be 0 here for the eigenvalue problem. So I could take, to get rid of this one, I could take 2i times the first row, add it down to the second row, make this one 0, and coincidentally this one will come out 0. If I take 2i times this and add it down, I'll add 4 down and cancel the minus 4. And I'll get a 0 row. So anticipating that, I'm going to just say, when I add multiple this down, I get this equals 0. So I just have the first equation, minus 2i times u1 plus 1 times u2 equals 0 is what equation this represents out of the augmented matrix, recall. Now, how can I solve this equation easily? Sometimes it's more difficult than this because I'll have real and imaginary parts here. It's actually really easy if you just take the first component to be the coefficient of u2, and the second one to be minus the coefficient of u1, then you'll always get 0, right? Because I'll put 1 for u1, I get minus 2i times u1, and 2i for u2, minus 2i plus 2i is 0. So one way to always choose an eigenvector easily is just whatever the coefficient of u1, u2 is, put it in for u1, and put minus the coefficient of u1 for u2. And then this will come out to be 0. So I found an eigenvector, u1, to go with lambda 1. Now, I have to find a second eigenvector. Trivial. The eigenvalues come in conjugate pairs, so do the eigenvectors. Immediately I write down that u2 is the complex conjugate of this. Wherever I see a real number, I just write it. Wherever I see an imaginary number, I just write minus it. So 1 minus 2i must be the other eigenvector if I were to solve it in the same way. So that's why I say it's easier. Once you get one, the other one is the conjugate of it. Replace all the real numbers with themselves, the imaginary numbers with imaginary parts with minus themselves. All right. Now, having found those eigenvectors, let's see if we can solve this system of differential equations, because after all, that's what we were after in the first place. This first is all the vector, of course. So, here's where we were then. Once I find these two eigenvectors, and these two eigenvalues, 2 plus 2i and 2 minus 2i, you have to put the eigenvalue 1 with eigenvector 1 and eigenvalue 2 with eigenvector 2 for this to work. Then this is the general solution over complex valued vectors u1 and u2. This is all solutions, all complex valued vector value functions like that. But that's not sufficient. And when we're solving a real problem, we want the subset of those that are real. So what we do is we use Euler's formula. E to the I theta is cosine theta plus I sine theta, and e to the 2 plus 2it then comes out to be this. And right, this is e to the 2t times e to the 2it is cosine 2t plus I sine 2t. So we can write this one as alpha 1 times e to the 2t cosine plus I sine. And this one as alpha 2, e to the 2t cosine minus I sine. And so we factor the e to the 2t out of both of these. And now look what happens to the rest. If I break this into real parts and imaginary part, I'll take alpha 1 multiplies cosine, and alpha 2 multiplies cosine. Let's see. The real parts are, if I take cosine times 1 and cosine times 1 here, I've got alpha 1 plus alpha 2 cosine. And then the imaginary parts, the part with I is I've got alpha 1 sine times 1, and alpha 2 minus I times 1. So it's alpha 1 minus alpha 2 times sine for the first component. Similarly, for the second components, now cosine times 2i becomes imaginary, so you get one of the cosines here. And then I sine times minus 2i becomes 2 sine. So I've got alpha 1, I times I is minus 1, times 2 is minus 2 sine, all times alpha 1, so there's minus 2 sine alpha 1. And similarly, minus I times minus 2i is minus 2, multiplies alpha 2, so you get alpha 2 times minus 2 sine. And then the imaginary parts, or if you take cosine with the 2i, or minus I sine with the 1. And you wind up with this real and this imaginary part. This is all the terms that include I, and this is all the terms that don't include I. Just quickly grouped there. Sometimes it takes a couple steps in between to check that carefully. But now that I've got that, what do I remember from what we said before? The real part is a solution. This times e to the alpha 2t, e to the 2t. And the imaginary part is the solution. Leave off the I. The imaginary part is what multiplies I. This times e to the 2t is the solution. So what I simply do is I take e to the 2t cosine minus 2 sine. That's one solution. I multiply by alpha 1 half, which is alpha 1 plus alpha 2. I let alpha 2 half be defined to be alpha 1 minus alpha 2 times I, and let that multiply this vector. And this times e to the 2t is a solution, this times e to the 2t is a solution. An arbitrary linear combination of those is the general solution still. If we let these be arbitrary complex numbers, we still get all complex solutions. All we did was rewrite this. But now, e to the 2t cosine of 2 sine is real. E to the 2t times this one is real. And what we realize immediately is that the subset of these things that are real valued are obtained precisely by choosing alpha 1 tilde and alpha 2 tilde to be real. So that we can get all, by rewriting it this way, it becomes evident what the real solutions are, just this, where alpha 1 tilde and alpha 2 tilde are any real numbers. So that's how we get the general solution to a system of 2 equations and 2 unknowns, homogeneous constant coefficients, when the eigenvalues are complex conjugates. Do the same thing we usually do. Alpha 1 e to the lambda t u1 plus alpha 2 e to the lambda t u2. But then break it up into real and imaginary parts, something with all the terms without I and all the terms with I. Then the real solutions are the terms without I. They just replace alpha 1 plus alpha 2 with alpha 1 tilde, this one with alpha 2 tilde, and you get, by restricting these to be real numbers, all real solutions. Well, once in a while, you get a system that has pure imaginary eigenvalues, right? Well, let's look at this system, for instance. The eigenvalues turn out to be plus or minus 4i if we work them out in the same way. And the corresponding eigenvectors found in the same way are 2i and 2 minus i. Find the general solution of this system. Well, we know what it is. It's e to the lambda 1t u1 plus times alpha 1 plus alpha 2 e to the lambda t lambda 2t u2. Now that's overall complex valued solutions. Once again, we multiply this out. We replace e to the 4it with cosine 4t plus I sine 4t. E to the minus 4it is cosine 4t minus I sine 4t. And so this is what it comes out to be in terms of using Euler's formula. That e to the I theta is cosine theta plus I sine theta. Now we can break this up into real imaginary parts, right? With the constants out front. Alpha 1 plus alpha 2 multiplies cosine times 2, cosine times 2. So it's alpha 1 plus alpha 2 times 2 cosine 4t. The imaginary parts, the parts with I in them, come out to be these. And if we then replace alpha 1 plus alpha 2 with alpha tilde 1, and alpha 1 minus alpha 2 with alpha tilde 2, we can rewrite all solutions in this form, and this is the same set of solutions that we had up here. The real valued solutions are the subset where you choose alpha 1 tilde and alpha 2 tilde to be real. And what you find out in this case where the eigenvalues are pure imaginary is that you get oscillatory solutions. There's no exponentials in here, it's just cosines and sines. This will just wiggle with period 2 pi over 4, it turns out. Will be our solution. Finally, the last problem, what happens if two eigenvalues are real equal eigenvalues? Sometimes nothing. What we said before is if you get independent eigenvectors, then you're done. You just write down that solution. C1, alpha 1 e to the lambda 1 t times u1 plus alpha 2 e to the lambda 2t, u2. But sometimes when you have two equal eigenvalues, you only get one eigenvector for them. And in that case, you've got a problem, right? You can't write two independent solutions. So what do? Well, by the theorem we did, still one solution is e to the lambda t times v or u, the corresponding eigenvector, just like before. We just have to find a second one. It turns out, and I'll leave out the theory on this, but the second solution, you can plug it into C, is t times the first eigenvector you found plus what's called a generalized eigenvector, all times e to the eigenvalue t. So you just have to take t times eigenvector plus generalized eigenvector times e to the eigenvalue t to get a second solution. And then, of course, your general solution is C1 times one solution plus C2 times the other. And you can do this for higher order systems. If you have a 3 by 3 matrix and it only has one eigenvalue, one independent eigenvector, you can use higher order generalized eigenvectors. We won't do this in this class, we're just doing 2 by 2, but I just wanted to mention. You can take t squared over 2 factorial times the eigenvector plus t times the generalized eigenvector plus a second generalized eigenvector of even higher order, all times e to the lambda t, and get a solution that way. So I'll just point out this extends to higher order systems when you only have one independent eigenvector and multiple other vectors you have to deal with. Alright, so let's see if we can find a generalized eigenvector. The generalized eigenvector, I need to point out, has this property. You find it by solving this equation. If lambda k, assuming you have a whole lot of eigenvalues for a big matrix, lambda k is an eigenvalue of multiplicity greater than 1, and we have a corresponding eigenvector vk, and we need a generalized eigenvector because there's multiplicities demand it. What we do now is we solve A minus lambda identity WK2, I'll call it, equals VK. This VK is called is in some sense a generalized eigenvector of order 1, so we'll call this a generalized eigenvector of order 2, is a vector that satisfies A minus lambda I times the generalized eigenvector equals the eigenvector you do have. And there's a larger definition of what a generalized eigenvector is, but we need the particular generalized eigenvector that satisfies this equation. So let's see if we can do that for this problem. And if we find this vector, we just write down that solution that we showed there. Here we have an eigenvector 3, 2 for this matrix, 4 minus 9, 4 minus 8. So I want to solve with eigenvector -2. Here we had the eigenvalue. The eigenvalues are -2 and -2, both equal here, and it turns out there's only one eigenvector. We said we solve A minus lambda identity W equals B. I'll solve for W12 because I'm solving a generalized eigenvector corresponding to eigenvalue 1, generalized eigenvalue of order, eigenvector of order 2. Meaning I'll get an eigenvector when I put it in. So A minus lambda IW equals B will solve for the generalized eigenvector. Now, here's A minus lambda times the identity with eigenvalue 1 equals -2 times W equals, here was our one eigenvector we have. That's this system, right? 4 minus the -2 gives me 6, minus 8 minus the -2 gives me -6. So I have this system to solve for generalized eigenvector W. Well, I don't know how to solve systems of linear equations, right? I just try and use elimination. So I write this in augmented form with the 3, 2 across the after the bar. And I can eliminate this, make it a 0 by taking -2/3 times row 1 and adding it down to row 2. And when I do, I get 0, right? That's what I wanted. But also, coincidentally, these will come out to be 0, leaving me with only one equation. That one equation says 6W12 first component minus 9W12 second component equals 3. That's what it says. And I can choose any components that satisfy that whatsoever. So there's a big choice here, actually. The easiest thing I think you do is you pick one of them equal to 0. Suppose I choose the second component equal to 0. Then I have 6 times this one equals 3. This one must be a half. So one solution is to choose the vector 1/2, 0. That is a generalized eigenvector corresponding to this eigenvector. So that's what's done on the handout there. Is I've picked this generalized eigenvector. It is a vector that satisfies A minus a -2I times W equals B. Any vector you want. Now, from the comment we made before, it's a theorem that we won't prove. It's better if you have a little linear algebra. You take T times the eigenvector plus the generalized eigenvector corresponding to it, all times e to the -2t is a solution. You can plug it in and see. That is independent of the first solution, e to the eigenvalue eigenvector. Now that we have two linearly independent solutions, we remember from the theory at the beginning that alpha 1 times one solution plus alpha 2 times another is the general solution. That's what you do when you have two eigenvectors, two eigenvalues equal, and it happens to be that there's only one corresponding eigenvector.